Thank you very much. Today I will talk about something that I don't know a lot about. And this is because we have just discovered something. We try to understand as much as possible about this thing. So I will share with you what we know. But then I hope you will get excited enough to continue studying on this topic as I am excited about it. No disclosures. So as you already know, TMS-EEG is a technique that combines TMS and EEG. So we stimulate with a magnetic stimulator. It's a transcranial magnetic stimulator, and try to activate transcallosally the cortex, while we are introducing as well plenty of artifacts. This is a typical response that has been already cleaned in the beginning, but this response has also some issues. After the stimulation, which is the red area, we have usually different artifacts, which is the main one is the pulse artifact, there is the decay artifact, and then there is the muscular twitch. The muscular twitch is usually due to the stimulation of the cranial muscles, but we will come later to it. And then there are late artifacts, which come after 20 milliseconds after the stimulation. And this is due to the auditory stimulation. It's a click of the TMS coil. Then we have the skin sensation, so it's the somatosensory, but we also have a lot of other unexpected possible inputs, which are due to the different muscles contracting on the skull, as we said before, or because if we are doing a motor evoked potential study where we stimulate the motor cortex, the feedback from the hand activation will affect also the cortex. Now, a lot of studies have been done to try to understand the blue part of this drawing. But the red part has not been investigated as much. The problem of the blue part, somehow, so the late response, is also that we have the co-activation of multiple sources in EEG. And as I said before, it's very difficult to disentangle this activity. So what we usually is, what we see is it's a peak, which is a mixture of different components. In our case, we were interested to see what happens in this first part, in this red part from the previous one that I decomposed further here in a cranial muscle artifact and in the pulse decay artifact. The decay artifact can be somehow controlled, but it's still a problem because it's a charge of the electrodes after the magnetic pulse. The cranial muscular artifact and the pulse artifact are the main topic here until we get to the novelty. So we tried to not to clean the pulse artifact because I tried it for many years and it doesn't work so far. What we tried to do is to shorten it. And recent advancements in the field of the amplifiers, EEG amplifiers, give us the opportunity to have a very high sampling rate. The high sampling rate means that we have to filter less before sampling. And filtering introduces a prolongation of the artifact to later milliseconds. And this affects our first responses. If we want to see the first response, if we want to see the activation of the local area that we are interested in, to see how this area then spreads the activity further, we need to shorten as much as possible this artifact. And we did that by using a sampling rate of 50 kilohertz instead of the standard 5 kilohertz. The standard 5 kilohertz have the artifact as seen in the upper right side, which lasts up to 5 milliseconds. So the first 5 milliseconds are usually covered. The muscular twitch. This is another artifact that is very problematic in TMS-EEG. And it's due to the fact that TMS activates nerves or muscles on the skull. This provokes a twitch of the cranial muscles, and this twitch, as you can see, affects the first 10 to 20, 30 milliseconds of the response. Depends on how is the intensity of the stimulation and how the coil is close to the, how much the coil is close to the muscle. And you can see that there are some regions that might be less affected. So we tried to use this by trying to find the best position of the coil to stimulate the brain region, which in our case was the motor cortex, without having the muscular artifact. We also usually have experiments, I have to mention that. We have experiments with subjects that have a lower motor threshold. This means that the intensity of the pulse, of TMS pulse, is lower. And lower intensity means that I am delivering less energy to the muscles or to the skull, and there is less probability to activate them. So if we, using this method of tilting the coil and finding the best position, usually tilting the coil towards the central part of the skull, we achieved to move from a very messy artifactual signal, which you can see here, to a cleaner signal which does not contain anymore the muscular twitch artifact, and you can see this also on the base of the topographies. So here we are. This is the novelty. And I will tell you what we know about it, but still, we don't know a lot about it. This is the first response that we can measure so far in TMS EEG. It's the earliest possible so far. It comes from 2 milliseconds on, lasts up to 5-6 milliseconds. It's a slower way where a higher frequency waves are superimposed. When we saw it the first time, we thought it was an artifact. So we did a series of experiments to see whether this is an artifact. And we cannot associate this response to any artifact known before in TMS EEG field. So this is why we hope that this first response at 2 milliseconds might actually tell us more about the excitability of the local region that we are stimulating. So among other tests we have done, we tried to see how the TEP, the i-TEP, which we call the name comes from the immediate transcranial evoked potential, how they relate to the stimulation intensity. On the left side of the screen, you can see that we have stimulated all the subjects at 110% of the resting motor threshold. And each subject obviously has a different resting motor threshold. So the amount of stimulation was different per subject. And you see that there is no relationship between the amount of stimulation and the response. So the amount of the stimulation delivered by the coil and the response is unrelated. On the other case, it's related in the single subject, in the sense that higher we go with the stimulation, you can see to the right side, higher we go with the stimulation, higher is the response in the single subject, which, in a sense, might tell us that this is not an artifact due to the electromagnetic induction. Then we also try to see whether we would see the same response in other cortical regions. So we moved the coil in other regions, and we saw it only when stimulated in one hand. Now, don't take this as a rule. We did not adjust the stimulation based on other regions, because our only goal here was to see whether it's an artifact. So we wanted to see whether with the same stimulation intensity, without adjusting the directionality of the coil or the position of the coil based on the cortex below, whether we would have the same response, and we don't have it, which means that it's a site-specific response. And that to have it, probably we need to adjust our stimulation intensity, position, and current direction. But we haven't done that because it's still unexplored. i-TEP depend on the current direction. So maintaining the coil in exactly the same position, just reversing the current, caused a different polarization of the artifact, as you can see here. Oops, that was fast. As you can see here, the direction of the artifactual response was reversed as the current direction, while our response in the, of the i-TEPs didn't change the polarity. And another thing is that when we were stimulating with the same intensity, the second direction, the less favorable direction, then the response was much lower. Then we had to adjust the intensity on the new direction to have the same level of response. And this actually follows the rule of the directionality that has been seen when stimulating motor cortex to evoke motor evoked potentials. So when we stimulate with the optimal direction, we have a certain response. When we stimulate with the opposite direction, the response is lower, exactly like here. So this talks in favor of a physiological signal. But is it a physiological phenomenon? Has ever been seen something similar? So we went through the possibilities to what are the options to describe what we see. And one thing is that it's already known that when we stimulate the motor cortex in epidural invasive recordings, it has been seen that there are responses that have similar frequency of the one we saw in the i-TEPs. So the i-TEPs have this high frequency response on the top, which is, has been shown also in the paired pulse TMS protocols, where if we give two pulses one after the other, where the first one is the over motor threshold and the second one under motor threshold, the second one can influence the first one, giving a shape here of higher facilitation at the different intervals, and this shape has a similar frequency to the epidural responses, the I waves, or the indirect waves. But then the question was, has it ever been seen in EEG, something like this? Yes, actually, because the somatosensory system, when it responds to the peripheral nerve stimulation, the first response of the somatosensory system is again a slower wave with high frequency peaks on the top. And they resemble actually the i-TEPs, as we can see. Same slower wave with the peaks on the top. And previously, we have already demonstrated that this high frequency in the somatosensory cortex and the high frequency in the motor cortex, evaluated again with SICF, short interval intracortical facilitation, they are related. And they are related also to the amount of the myelin in the specific cortex area. So in summary, what I wanted to show to you is that we have found something new. We are super excited about it because it's the first time that we can measure a response in the brain after 2 milliseconds after TMS stimulation. And if this is the case, if this is true, that this is a cortical response, then for the first time we can see the local excitability of a brain region. We did it on the motor cortex, but everything else is unexplored. And also, what are the generators? How this actually, what is this information giving to us? How we can use it? It's a completely new world for us. And I hope you get also interested into this and start working on that with us in the future. Thank you. And if there are any questions?
Yeah, thank you, Leo. Are there any questions from the audience? No? Marta, do you want to ask something about the early latencies? I don't know.
Thank you, Leo. This is very, very interesting. I have a lot of questions. We have also been working on these i-TEPs after you published the preprint, and at least I can say we see it as well. But I think, and you might agree, at the moment what we are missing is a physiological effect. So I guess this would be like a very important evidence that is indeed a physiological response from the brain. Have you considered some conditions in which you could see a modulation of the i-TEPs?
Yeah, this is a good question, and you know the answer. So the thing is that since we don't know what are the generators, we would like to perform some experiments where we can manipulate the excitability of the motor cortex in order to see modulation of the i-TEPs. Unfortunately, we have not done experiments that can show us the modulation of the i-TEPs so far. There is also, the question is also, we don't know what they are showing, so we will try different possibilities, and the idea is to show when they are modulated and whether they are modulated by something, but also when they are not modulated, to understand what they represent. We have done some tests with motor contraction, and we haven't seen a modulation, but you know that because you also did the same. Yeah. The good thing is that I would say that the first good thing is that they have been seen in other laboratories. And now it's, I would like to know if we can find a way to see whether they are modulated and by what they are modulated. I guess that, that a natural thing would be a pharmacological study with GABA to see whether how this influences.
Yes, thank you. So maybe I have also a kind of a technical question. I don't know whether it's really technical, but given that you can now sample like our data with such high sampling frequency, so do you think that one could go and try to look also for the high frequency oscillations in this data, the HF4 that you have shown in your result? Like the 600 Hertz.
The i-TEPs are around 660 hertz.
Oh, okay, they already,
They are.
okay.
So this is why I compared them to the high-frequency oscillations and the sensory system, because it's a very similar frequency. It's around 660, 690 hertz.
Okay, thank you. So I don't see any other question on the app, and maybe not even from the audience. So we thank Leo once more, and yes, and we go on. I think you take the role as a moderator and introduce Umair, right?
Yes. So